and other aspect of communication in 5G, 6G related areas. Professor Pradhan did his PhD in signal processing from IIT Bhubaneswar, and postdoctoral research he carried out at Mayo Clinic, Arizona, United States of America. After that, for more than 1 decade, he continued his research at IIT Roorkee. He guided several research projects successfully completed, and he has numerous publications in various IEEE, Elsevier, and Springer peer-reviewed reputed journals. Professor Pradhan is a member of IEEE, and he has supervised several research theses at IIT Roorkee in the area of signal processing and communication. So over to you, Professor Pradhan, for today's talk.
Thank you very much, Professor Nanda. Thank you to all of the volunteers, all the participants who have enrolled for this program. Let me share the slides. So is this visible?
Yes, please make it full screen.
Yeah. So is this okay now?
Yes, perfectly fine.
Fine. Okay, fine. So should I keep the video on or?
Yeah, you can keep the video on.
Okay.
The participants will be writing in the chat box.
Fine.
If they will have any queries. So at the end or in between also, whenever you like, you can take their questions.
Okay,
also,
fine.
it is a 2-hour session. So whenever you wish, you can take break also in between.
Okay. Thank you.
As per your convenience, there is no problem. You can take 5 minutes break, take some water, and then again resume the session. There is no problem. Up to 2 hours. Anytime you can take questions or the things on the chat box, but they will not directly be interacting with you.
Fine.
They
No
will
issues.
be writing on the chat box. Okay, so that
Sure.
your flow will not be disturbed during the presentation.
Okay, fine. Thank you.
Okay.
Very good afternoon to all the participants. In this today's presentation, I am going to discuss regarding IoT networks, and my major focus would be on the data protocols. Now, how these are relevant to the 5G and beyond wireless communication challenges is when we look at the 5G and 6G and further generations, we normally think about cellular communication based aspects. But if you look at 5G, 6G and future generations, you will see that there are a lot of emphasis on your industrial applications, IoT applications. If you look at your cellular communication, there is of course a big chunk of research going on in that area. But apart from that, if you look at Industry 4.0 and above, you'll see that there are a lot of people trying to bring in 5G and 6G into these areas. Okay. Looking at the industrial aspect of the 5G and future generations, I'm going to discuss some of the protocols that we practically use for communicating the data between the nodes or between the users or between the clients. Okay, let me start with some basic info regarding the IoT networks, not much in detail. Now, a lot of literature is available over the internet related to the numbers related to IoT networks. So I'll just briefly touch upon the basics and then move on to the focus topic, that is data protocols. So, mainly I would be covering IoT in general, and then my major focus would be on IoT protocols. Then I'll show you a comparison between different IoT data protocols. And in fact, I'll show you a case study that we performed in our lab using low-cost microcontrollers, which you can also try yourself to see how these data protocols perform in real time and what are the limitations of each of these data protocols. So you can have very simple experiment to check those parameters. So when you look at the IoT, which is way popular now, we not only look at the IoT in terms of sensors, we also look at the IoT in terms of applications and the integration of sensors with the applications. Now, we know that we can use various types of sensors, and in fact, if we look at the day-to-day used sensors, such as temperature sensors, pressure sensors, the amount of data that they collect is vast. So when this large chunk of data are actually being transmitted to a server, there are various protocols that are used to transfer this data. In general, when we do research on algorithm side or signal processing side, we do not look much into the protocols. The inbuilt default protocols are usually deployed, but when we look at the industrial applications, these protocols have a huge difference in terms of practical performance. So we'll see down the line what are those performance measures based on which we can compare the performance. Uh, so basically, when we look at the IoT, it's a network of physical objects, and we are dealing with communication, we are dealing with sensing, we are dealing with interaction between sensors. Okay. So when we look at the industry definition of IoT, because I know there are a lot of people who do research in IoT, and the conventional way of dealing with IoT is to map it with the physical world. So what are the things that are happening in the physical world? Can the same thing be repeated in the information world? So for example, if you look at the left part of the figure, we have the physical world where we have devices, we have gateway, we have physical things, right? Can they be transferred to the information world where we indicate them using some kinds of bits and pieces, and then we link them using some kind of communication standards? So when we look at the IoT industrial definition, this mapping between physical and the virtual world is what the the IoT industry definition is. Okay. For example, in the physical case, industrial robots, goods, analytical equipment, sensors, gateways, all those. When we move into the virtual part, of course, we have application softwares, information content, multimedia content, all those are being mapped. So the next part is the the IoT network are widely used nowadays, but why these IoT networks are so popular? The first one is, of course, these are very open platforms. These can be designed very easily. There are plenty of literature available. There are plenty of standards available. So you can design it very fast. You can make it more secured. We'll talk about security in detail down the line. You can make it more accessible, right? And when we look at IoT, we generally deal with sensors in an IoT network. So when we talk about sensors, these sensors are deployed in various applications. We know, no, these are deployed in actuators, they are deployed in smart cities, USN applications. Okay, but then the amount of data these sensors are collecting is actually huge. So if I go on using the complete set of data, the amount of energy or the amount of battery power that is being utilized would be very high. So can we do something with respect to low power performance? Okay. So this IoT networks help us in designing or creating a low power network. Of course, it does have other contribution in terms of socio-economic development, because when we look at these IoT networks, these are highly popular in industrial applications. In addition to that, these are all can also be used in agriculture sector to monitor the big chunk of land. This is highly used in health sector in terms of body area network. Okay, there are a lot of applications of body area networks. And of course, when we look at your IoT, it is able to manage the utilities much efficiently. So, for example, when we look at the smart grids, we know that a lot of smart grids are now being integrated with the IoT network, where you do have different sensors, you do have different power meters, smart meters. So those are being integrated with the smart grid using this IoT network. Similarly, you can also monitor water grids. You can also use IoTs in transport management. When we look at the smart cities, if you look at the traffic management in the smart cities, that can be easily done using IoT. So it does have a huge set of applications, and it is very popular for industrial applications. So, what are the different characteristics of IoT? Of course, they are highly efficient when we look at the industrial applications. The second advantage is a very big plus point as far as the performance is concerned, because today I have designed an IoT network with 10 sensors, and down the line I require 5 more sensors. Can the 5 extra sensors be included or be integrated with the existing network? Will it be able to support the 15 sensors? Will it be scalable or not? So because of this advantage of scalability, this is very popular in terms of industrial applications. Similarly, when we do when you deal with IoT networks, you're dealing with sensors. So every sensor does have some address. You have some MAC ID, you have some addressing architecture. So the way we were dealing with different devices in the physical world, now we know that these sensors can also be dealt in the same category. So every sensor can be differentiated from the other sensor in terms of MAC address, in terms of the architecture, in terms of the addressing architecture. Similarly, when we look at this IoT networks, we do have a scenario where it might happen that the sensor node is not required to operate throughout the day. So we do have different modes of operation for these sensor nodes. So either I can convert this sensor nodes from the running mode to a sleeping mode, where I can define the sleep cycle for few minutes or few hours, and then intermittently it should wake up, check the temperature or check the pressure, and then again go to the sleep mode, right? So that can be done using IoT networks. The other characteristic is mobility. So where not all the sensors are mobile in nature, but there are a lot of sensors which can be made mobile and then practically used in monitoring the areas. So there are a lot of IoT networks which helps us in managing this mobility. Intermittent connectivity. So there is no requirement of the sensors or the IoT devices to be connected continuously with the server. We can have intermittent connectivity with the server. We can save the power. Whenever it is required, it can actually wake up and then read the value and then send it to the server. So those things are possible with the IoT networks. Now, if we look at these IoTs, they are highly linked to Industry 4.0, and here is a figure where the x-axis is the intelligent connections and the y-axis is business and societal impact. So we can see that when we look at all these connectivity, network economy, immersive experiences, IoT, all those play different kinds of roles in this scenario. And there is a there is a figure on top which shows how the industry standards have changed over time. So, initially we referred to Industry 1.0, which was more of a mechanical side aspect. And then Industry 2.0, which was mass production. Industry 3.0, where the most of the control and electronics part were deployed. And then when we look at the Industry 4.0, that is where the IoT is being integrated with the the physical world. So the integration of IoT with the physical world actually leads to realize some of the applications which were not possible in the previous industry standards. Okay. So on the right side, I have specified two terms. One is the information technology, and the other one is operational technology, which was operational technology is more to do with the monitoring and controlling of devices. Information technology is where we look at the transfer of information from device to device, right? So this is more of a convergence between both the technologies, where typically, if you look at your information technology, it doesn't get involved with the production and logistics. But here is a scenario where the IoT can help us actually converge these two technologies. Okay. So if you look at the IoT general architecture, so this is a general architecture where so here is a IoT general architecture. So if we look at the cloud, that is your cloud storage and intelligence and analytics part of this architecture, and you can see there are lots of communication standards being deployed. You have wired communication, you have wireless communication, you have short range, you have large range communication. I mean, if you look at all the standards, you require lots of different kinds of communication protocols to deal with these standards. Okay, so we can see there are sensors, there are gateways, there are Bluetooth devices, there are different kinds of Wi-Fi devices. You do have LoRa devices where they deal with LoRa range. So we'll see how towards the end I will show you a picture where you can actually integrate various devices using different kinds of protocols. So we'll see that a single protocol can be used for all these communications, but then that would not give you the efficient performance. So the protocols would change depending on your application requirement, depending on the physical environment, what kind of challenges that you are dealing with. Okay, so there are various case studies that we will look at. So when we look at these IoT protocols, this is a figure which shows you the comparison between the conventional web stack and the IoT stack. Now, the conventional web stack is something which most of us have looked at when we look at the internet stack. Okay. The left hand side is the IoT stack, which is somewhat newer, somewhat different from the conventional web stack. But let's look at the major differences between these two stacks. On top of the architecture, you can see that the one of the major differences in terms of TCP/IP model, where you have an IoT application and you have device management. Whereas when you look at the conventional web stack, we only have web-based applications. Okay, so in web-based applications, you are not managing any devices, or you are not managing any IoT applications. So it's a web-based application. When it comes to data format, JSON can be used in both the cases. Okay, application layer, we'll see this application layer in much more detail down the line, because that is where your data protocols would show up. Okay, so these COAP, MQTT, XMPP, AMQP, all these protocols, I'll touch upon these protocols in brief down the line. But when we compare these protocols with the conventional protocols, that is your HTTP or TLS, you can see the performance comparison between these two sets of protocols. Why these protocols are so popular for IoT applications? We'll look at the difference between these two sets of protocols. When it comes to transport layer, of course, UDP can be used on both the sides. But here is another higher standard, which is called a DTLS. Internet layer, of course, IPv4 and IPv6 is used on both the sides. On top of that, as you might have heard about this low power wide area networks. So because you're dealing with sensor devices and they have a power limitation, so what would happen is we always prefer to have these devices utilizing as less power as possible. So that is the reason that we can now, in addition to the IPv6 and IPv4 protocols, we can also use this low power protocols for those applications where there is a real limitation in terms of the battery power or power management. Of course, network layer, we have MAC layer and physical layer protocols. So on the left side, you have the LAN and conventional Wi-Fi protocols. On the left side, you have 802.15.4 MAC and physical layer protocols. Okay. So my focus would be on this application layer protocols, where I will start with very simple protocol and then look at the practical scenarios that we face in industrial environment. So when we look at this IoT communication pattern, there are 4 standard patterns that we can see. The first one is the telemetry pattern, where the information flows from device to the other systems for conveying some change in the status of the device. Okay, so the top pattern that you see is the device sending some kind of status to the through this telemetry signal. Okay. The second one is the inquiry, where requests from devices are sent, okay, and some inquiry is made. Okay. The third one is the commands, okay, where you send the commands from other systems to a device. Let's say you send a command from your server to the sensor that you read the temperature and send it back to me. So that is your command pattern. And the fourth category is the notification, where you want to send some kind of information from the server side or from other system to a device or a set of devices, that okay, this environment has changed, or the protocol have changed, so the temperature has to be now recorded once in 15 minutes instead of once in 1 minute. Okay, so that is the notification that is being sent. Okay, so we looked at the IoT layers, and if you look at the different aspects of these protocols, these are the 8 different categories, you can say. Of course, the connectivity side, I have already told that one of the significant changes that happened in the connectivity protocols is the low power wide area network protocols. Okay. Identification, IPv6 can be used. On top of that, there are a few other identification protocols for dealing with the low power sensor devices. Communication standards, you can use Wi-Fi, you can use Bluetooth, and the third one is the low power wide area network that I was talking about. Discovery, you can use, you can discover the devices using the physical wave, which was there previously in the web stack, or you can also use DNS standards for finding the device. Data protocols, this is what I am going to focus on. The fifth one, that is the MQTT, COAP, AMQP, and XMPP. I will discuss in detail down the line. You can also have device management. You can have different kinds of semantics. You can have multi-layer frameworks. Okay, so these things can be the protocols are mainly categorized into these 8 types, but I will be focusing on the fifth one, that is data protocol. So when we look at this protocols, let's look at the evolution of these communication protocols. On the left side on top, you can see the conventional protocol where you have a device to device direct communication. So you have a point-to-point communication where you use either the TCP protocol or you have sockets. So you have one socket defined for one device, the other socket defined for other device, and there is a communication between 2 sockets. Or you can use 0MQ and COAP. I will touch upon COAP. The second kind of communication protocols that we can see is where the middle one on the top. So that is the publish and subscribe. So for example, if I am a client and if I have subscribed to only temperature information and not pressure information, then the temperature sensor data will only come to me. I will not get the pressure sensor data. So the the uh, the agent will take care of the management part where only those topics. So for example, temperature is a topic and then pressure is a topic. So only those topics are actually passed on to the clients for which the clients have subscribed. Okay. So that is how the publish and subscribe protocol is carried out. The third one, which is on the right, that is the third one on the right is the data centric public subscribe. That means there is a common bus, which is your blue arrow mark. There is a common bus having all the informations, but then so there is no requirement of any agent coming into picture. So there is a common bus. All the devices are connected to the common bus, but then whatever you have subscribed for, only that information will be provided. So from the bus, you can only access that information for which you have subscribed. Okay? But there is no management as far as the agent is concerned. This is a common bus. So this is a data centric scenario where, for example, DDS. Okay. The fourth one is the broker, where the broker is actually controlling the management part. So broker is having all the information, all the topics are with broker. So as a client, whatever a topic, whatever information you want, you have to pass it to the broker, and the broker will only allow that information to be passed back to the client. Okay. And this is where the client server mechanism comes into picture. So between client and server, you do have a broker. So MQTT, REST, XMPP, these are highly popular protocols as far as this broker-based scenario is concerned. The fifth one is the queuing one, where information is being queued, okay, and then based on whatever information is required, that is passed to the client. So there is a queuing mechanism as far as the fifth one is concerned. So whatever information is coming, that will get queued, and then first come, the first in, first out mechanism, or other three mechanism can be deployed to deal with the queue. So these are the 5 different architectures that can be used to handle these communication between clients, which are devices or sensors, and your servers or other devices, other systems. So let's start with the first protocol, that is MQTT, which is the simplest protocol that you can see, that you can find being deployed in most of the simple applications, not high performance application, but very simple applications in terms of the cost. Okay, so as the name suggests, the name is message queuing telemetry transport. So the data transfer is happening, that is telemetry transport, and there is a queue involved, and the messages are being queued and then transferred. Okay. Now, this was introduced by IBM back in 1999, but it got standardized way late in 2013. This is a very lightweight protocol. You can, now I'll show you the comparison between the protocols, but you'll see that MQTT is a very light protocol, and it is designed for very limited applications. For example, whenever you have a limited bandwidth, you would go for MQTT kind of protocol. When you require a very small code footprint, then you go for MQTT kind of protocols, or you're dealing with remote connections. So very simple applications where there is no strict restriction as far as the performance is concerned. In those scenarios, you can go for MQTT. This can be used for transport. It could be used for telemetry data, sensor data. There are a lot of applications where this MQTT is deployed. In fact, when you buy any IoT devices from the market, the protocol that they usually deploy is your MQTT when it comes to standard applications. So what are these special characteristics of your MQTT protocol? It's a machine-to-machine or device-to-device protocol. It's a very lightweight protocol. When I am saying lightweight, means in terms of complexity, the protocol is very, very low complex protocol. It does deal with the devices in terms of publishing and subscribing mechanism. So there is a client, there is a server, and there is an exchange of data, but then the client will only get that amount of data for which it has subscribed for. Okay, it's not that I have a IoT network where I'm recording, let's say, temperature, pressure, humidity, 3 data, but then this 3 data will not be available to each client. It depends on the client for which it has subscribed for. Only that information would be transferred to the client. But there is no requirement of the publisher and subscriber to be connected at the same time. So this is one advantage over the conventional scenario. In conventional scenario, if you are looking for temperature information, the sensor has to pass the temperature information to me, to the system, while being connected. But here is a scenario where the publisher and subscriber are not required to be connected at the same time for the transfer of data. So that means the information is already available when you are subscribing for the information. Of course, this is a very fast data transmission because of the low complexity, and the client receives data for only those topics for which it has subscribed to. So this is one of the restrictions that is put, that you have to have a subscription to get the data from the server or from the other system. So the MQTT, there are various components of this protocol. The first part is the message. Okay. So when we refer to message, what are the things within the message? So of course, the original payload data, let's say temperature or sensor, humidity or pressure, whatever payload data that we have. The second one is what kind of quality of service that we want. We'll see down the line that there are 3 types of quality of service, and based on the quality of service, the number of acknowledgements or the number of data transfers would change. So if you want very high quality of service, the number of communications would be much more. If you can manage with a low quality of service, then the number of communications would be low. And we'll see what are the applications which require different kinds of quality of service. A third one is the collection of properties, means metadata related to the message frame. And the fourth one is the topic name. So what the payload data has been put up, but what is that payload data? Is that no, the payload data would be in terms of some binary bits. So what is that payload data? So that is defined in terms of the topic name. Now, as far as devices are concerned, we do have clients, right? So here the users are also clients, and if you look at these servers also, they are also a type of clients, right? So the server is actually publishing the messages, and the users are actually subscribing to the messages. So you have a subscriber or you have a publisher, but both are part of the clients too. So what are the responsibilities that are shared between these clients? The first one is the network connection to the server has to be opened by the clients, publishing message which the other clients are interested in, or if you are subscribing the request messages that you are interested in. Okay, so either you are publisher or you are a subscriber, so one of the two. Unsubscribing to remove the request message. So for example, you have previously requested for temperature information and then you require pressure information. So you unsubscribe and then subscribe for temperature pressure information. And once your message has been received, you have to close the network connection to the server. So these are handled by the clients, whether as a publisher or a subscriber. These are the processes that needs to be carried out. And the intermediate person that is going to handle the scenario is the broker. Okay, so this is the intermediary between your publisher and subscriber. Okay, now what are the responsibilities of the broker? Remember one thing, that here is a case where the subscriber and the publisher are not directly connected, and they are also not supposed to be, there is no requirement of them to be connected in real time at the same time. Okay. So the broker is actually handling that kind of scenario where it accepts the network connection from clients, it accepts application messages published by the clients. So whatever publisher has published, that is also with the broker. So it processes subscribe as well as unsubscribe request from the client. So there are two stages. First, you have to subscribe to certain topic. Once that is approved, then only you start getting the information for that particular topic. Okay. Forward the application messages that matches with the client subscription. So temperature data, metadata has to match with the temperature metadata that the broker has. Then only the topic is matched, and then the subscription will work. And of course, once the data transfer has happened, then you close the network connection. So you can see on the left side, we have a publisher which is publishing the topics. The topics could be, so the publisher could be some device which publishing temperature, pressure, or some kind of information. That is the topic. Subscriber could be any client and any user. Even the server can also act as a client. So this is a simple example of an architecture where MQTT is deployed. We have 3 subscribers and we have 2 publishers. So the 2 publishers are providing the information to the broker. And once the information is with the broker can distribute the information to the subscribers. But keeping in mind that whatever topics have been subscribed by the subscriber or the client, only those information will be passed on to them. Okay. So if you are not subscribed for pressure, you will not get the pressure data, although the pressure data and temperature data are recorded simultaneously. So what are the topics that we are talking about. So when we talk about publishing a topic or subscribing a topic, so there are different layers of hierarchy, okay, and there are different wildcards. So for example, the figure shows an example of how to create the topics. So let's say we have building 1, which is the bigger umbrella, and within building 1 we have floor 1 and floor 2, and under each floor we have certain number of rooms, and within these rooms there are certain number of sensors, say temperature sensor, humidity, in one room, and room 2 does have only temperature sensors. Similarly, room 1 in floor 2 has only humidity sensors. So how do you define the topics? So for example, you can see the example building 1 slash plus room 1. So that means irrespective of which floor, you are now looking at building 1 and room 1. Okay. Similarly, I can refer to building 1 slash floor 1 slash room 1 slash HAS. HAS means all the sensors that are there within room 1. So both temperature and humidity sensors come into picture with HAS. So HAS and plus, these are the wildcards, two wildcards that are used to notify the topics. So every message includes a topic that classifies it. So MQTT servers use these topics to determine which subscribers should receive messages published to the server. Now you can see an example where no, the top label is your my home, and then you have subsequent hierarchy labels. So, and each of these labels are separated by your slash. And we saw in the previous example that is building 1 slash something slash something. So slash is your separator between different labels, and within those labels you can define specific instances. So and when we look at the number of topics, this is an example where we are looking at temperature sensor. But if I want all the sensors that are there in the living room, I can use has to represent, to access all the sensors within the living room. So if I put my home slash ground floor slash living room slash has, that means all the sensors within the living room can be accessed. So that means I have subscribed to all the topics that are there within the living room. Okay, and the topics are case sensitive. So your capital T temperature and small t temperature, they are different. And the reason, no, the reason this is also this is advantageous because the number of topics that can be generated using this small letters and capital letters are huge. So this also allows you to deal with multiple topics, the large number of topics that can be addressed. Additionally, the forward slash itself is a valid topic too. So if you put a forward slash, that is also considered as a valid topic. So when we look at this structure, this is an example where we have a publish and subscribe uh, scenario, where we have on the left side we have a PM sensor and a temperature sensor, which are actually publishers. Okay, so the Ameva PM 2.5 sensor is publishing the data, PM data, that is 17 UG per meter cube. Similarly, a temperature sensor is giving a data of 25 degrees Celsius, and these data is being passed on to the MQTT broker. On the right side, we have two clients. One is a laptop and one is a cell phone. And the laptop has subscribed only to PM topic, so it is only getting PM data. Similarly, the cell phone has only subscribed to the temperature data, so it is only getting the temperature data. Okay? So the job of the broker is to make sure that whatever the clients have subscribed to, only those topics are being passed on to the clients. Okay. So what is the message format that is used? So I'm going deeper, little bit deeper into MQTT because when you practically use IoT devices, most of the devices in the first class use MQTT unless you modify the architecture. Okay, so when you look at the message format, on the left side, I have this MQTT clients, which can be a laptop, could be a cell phone, could be a server. Okay. On the right side, I have the MQTT broker. So when you look at the conventional physical world mechanism, similar mechanism is also followed here, that the first part is the clients connect to the broker. Okay. And then subsequently, they get the acknowledgement from the broker. The third one is once they get the acknowledgement, then they will subscribe to whatever topics they want. The broker has to first give an acknowledgement saying that, okay, you have subscribed to 2 topics out of 5 topics. So that acknowledgement has to be given. And if you are a publisher, then you publish the topics to the MQTT broker. So as far as publisher is concerned, you don't have subsets of topics that you are going to publish. Whatever topics you are publishing, you just push it to the broker, and the broker will give you an acknowledgement saying that these are the topics that I have received from you. So when we look at the packet structure, we have different kinds of headers. One is the fixed header, which is present in all kinds of MQTT packets. Okay, so that is the figure is shown below, and there is a variable header which is present in some MQTT packets. Okay, so depending on what kind of message type, you'll see that the variable header might be there, might not be there. Of course, payload will always be there. So whatever data that you are collecting, that would be kept in the payload part. So that is the packet structure. The second figure shows the message structure, and so there are 2 bytes. Fixed header. If you look at 2 bytes are fixed. Rest depends on the message type. So what is this fixed header? The fixed header is byte 1 is MQTT control packet type, and what are the flags? We will look at the flags in brief. And byte 2 is the remaining length where you handle the addressing part. Okay. So there are 2 bytes which are fixed, and that is used in all kinds of packets, all kinds of MQTT packets. Okay. So here is a table which gives you the comprehensive list of message formats that are used for the communication between devices and or clients and broker or clients and servers. Okay. Value 0 is forbidden, and then you do have 1 to 15 which are dealing with some kind of acknowledgement, some kind of release, some kind of completion, some kind of request. Okay, so the different kinds of commands are written on the first column. Last column shows you the description. Among them, you will see that there is something called as QoS, that is quality of service. We will look at the quality of service in brief down the line with few examples, which kind of application comes under quality of service 1 and which kind of application comes under quality of service 2. Or now, when we look at this MQTT, these are the control packets that you have. Okay, there are 4 bits which are used to handle these flags. Okay, so you can see the fixed header flags. Most of them are reserved flags, and only the publishing part, which is used in MQTT 5.0 and above, that is where you have 3 different flags. That is, one is DUP, that is indicating what is the duplicate delivery of a published packet. So that depends on the quality of service. So that is the reason that the next one is QoS, that is quality of service. So depending on what type of quality of service you want, Based on that, whether there will be duplicate delivery of the packet or not, that would be decided. Okay. And the third one is the retain, that is publish retained message flag. So whatever message flag that you have written, that has to be published. So except that row, you can see rest other flags are actually reserved flags, and you can see the commands on the left, in the first column. So all the acknowledgement, all the subscription, all the release, and publishing part are shown. The fourth one, which has been written in the italics, is malformed packet. So if there is a packet which has malformed, and that has to be also informed. So this invalid packet received has to be also informed. So depending on whether the quality of service is high or low, there would be another duplicate packet being sent or not. Okay, so we'll see whether this quality of service is 0 or 1 or 2. Based on that, this repetition of the packet would happen. So except those 2 bytes, whatever remaining length we have, that is your length of the variable header. And I said this variable header is not mandatory, okay, but the payload is always there. So length of the payload will always be there, but variable header is might be there in certain packets, might not be there also. Okay, so the variable header is 10, length of payload is 20, then remaining length will be 30. Now when we look at the payload is the major information that you are dealing with. So all the data that we are dealing with, that would be a part of the payload. So what are the components of the variable header? So this this lies between your fixed header and your payload. So this is your variable header. Now this, so depending on the packet type, the variable header would change. Now the list of packets are shown below. You have either publishing, or you are acknowledging, or you are releasing, or you are receiving, right? Or you are subscribing, unsubscribing. So based on the packet type, you'll have different kinds of variable headers. And of course, the quality of service comes into picture when we define these headers. So the last part of this frame is your payload, okay, where your data is there. So the final part of the packet for some control packets, this is the data which is being practically sent, and the list of MQTT control packets are shown, and the payload is shown in the second column. So if you are connecting, then a payload has to be mentioned. If you are getting an acknowledgement, you do not require a payload, which is practically true, that if I am connecting, I require a payload. I do not require a payload for acknowledgement. If you are publishing, that is optional. Any acknowledgement doesn't require any payload. Okay, if you are subscribing, then you require payload, because if I am subscribing to only temperature or only pressure, that should be known to the broker. Okay, but if I am publishing, I might publish, I might not publish. So it's not necessary that I need to have payload in my frame. But if I am subscribing, I do have to specify what kind of payload I am looking at. For subscription acknowledgement, you require a payload, because the acknowledgement is with respect to what topic I have asked for. Okay. Similarly, unsubscribe and unsubscribe acknowledgement. REST 4 do not require any payload, because they are the initiation control packets. You send a ping request, you get a ping response, or you disconnect, or you authorize in terms of security. So those do not require any payload. So this is the overall figure that we have as far as the message format is concerned. The first row shows the bits. So 1 byte is your 8 bits, so 0 to 7. So the first byte is already shown. DUP is duplicate. QoS, your quality of service. Retain is what kind of flag you're returning. That information is there. Byte 2 is your remaining length. byte 3, 4, 5, it goes on based on what topic we have referred to. So that would be part of your variable header. And the last one is your published message, which is your payload. So the topic name and topic name string length, no, the first 2 bytes are used. The message ID is present if your quality of service is 1 or 2. Similarly, publish message. Okay. Now, I have spoken about these 3 flags, which are very important. These are whether you want to have a duplicate flag to be 0 or 1, and the quality of service and retain. Okay. So here are the 3 quality of service, that is 0, 1, and 2. Quality of service 0 is at most once delivery. So that means whenever the packets are sent, the packet would be sent to the client. You do not expect any confirmation for the packet. So at most once delivered. So whether it reaches the client or not, I don't care. Okay, so that is your quality of service 0. You can improve the quality of service to 1, where you say that, okay, I want my packets to be delivered at least once. So that means I will send one packet, I will expect acknowledgement. If I do not get an acknowledgement, I will send another packet. So it might happen that the first packet has reached the client, but I haven't received the acknowledgement. So that means I have sent the second packet. So that is your at least once it has been delivered. Okay. The highest quality of service is the most complex one. That is, I want my packets to be delivered exactly once. So the amount of acknowledgement or amount of command signals that are involved are much more in quality of service 2 as compared to 0 and 1. Okay. The fourth one is not used, that is reserved for the device. That is the if you have 1 and 1, that would create a problem as far as the message format is concerned. So that is the reason that 1 is actually avoided for quality of service. So duplicate flag, you can see that the phrase or new publish has to be set as 0. And if you are going to redeliver the topic, then it has to be 1. And remember that it has to be redelivered only when the quality of service is 1 or 2. In quality of service 0, you are not going to redeliver any topic. It has to be just sent, and you move on to the next packet. The third flag is your return flag, where if your return flag is 1, that means the application message is stored. And if your return flag is 0, then the application message is actually not stored. So let's look at the examples of quality of service. Okay. So let's say the first quality of service label is 0. So as I said, you expect at most once the packet should get delivered. Okay. So the messages are delivered according to the delivery guarantee of the network. So you don't have any control over that. You are not expecting any response, and you are not going to retry the packets. Okay. So this is the lowest quality of service that you can expect. Okay. But then what are the applications where these are highly useful? Say, for example, you are recording temperature throughout the day, and that data is regularly getting published. So even if, let's say, every 1 minute or every 30 seconds you are generating temperature data, then even if 1 or 2 packets are lost, you don't worry, because that means that information is not going to have a big impact as far as the application is concerned. Okay. So if you're regularly publishing some temperature data, you can easily use the lowest quality of service, that is 0. If you are following this protocol, of course, this is the fastest way, because you are not expecting any acknowledgement. So you have just published the topic, or you have just published the data, and then you delete the message. You don't care whether it has reached the subscriber or not. Okay. So the broker will receive the data and it has to publish to the subscriber, but you don't care whether it has reached the subscriber or not. So the message can get lost if the subscriber is unexpectedly disconnects or if the broker fails. But then since you are not getting an acknowledgement, you don't care whether the topic has been received by a subscriber or not. The second quality of service is at least once delivered. So that means it should be delivered to the subscriber at least one. So that means there could be duplicate topics or duplicate data being sent, but at least it should receive one packet. So if the publisher did not receive, then the publish act. So PUB ACK is publish acknowledgement. So you will not receive the publish acknowledgement on time. So you will send a duplicate packet. Okay, so you resend the message. What are the examples? For example, your door sensor that is sending the state of the door or the status of the door, whether it is closed or open. Now, say for example, your door remains open, okay, and the first packet was sent, but the acknowledgement was not received. So the sensor will send a duplicate packet saying that the door is open. So even if you get multiple packets saying that my door is open, the application is such that this is not going to affect. But keep in mind that I require the status of the door to be open so that the door is open and you go and close the door. But so that information is required. But even if I get multiple packets of the same door status, it is not going to hamper me. This is a typical example of quality of service level 1. So below you can see the flow. That is, the publisher is storing the message. It is publishing. Once the broker receives the message, it stores the message. It then publishes, okay, to the subscriber. Then it deletes the message, and then it sends an acknowledgement. Then only the publisher will delete the message. So unless the publish acknowledgement is received by the publisher, it is not going to delete the message. It will initiate the second packet. Okay, so this process goes on until the publish acknowledgement is received by the publisher. So that is the reason that you could have duplicate number of packets being received. So doorbell, alarms, all those examples are typical examples of quality of service level 1. The third one is the high performance applications, where you want your packet to be delivered exactly once. You do not want multiple packets. Okay. For example, let's say sounding an alarm as a reaction to an event. So let's say there was an event and you want an alarm to be there. You do not want that alarm to be continuously, the alarm to continuously go on with repetitive packets. Once you want it to be received by you perfectly once. Okay, so that is why the quality of service is very, very high here. That is 2. So this is the highest level of quality of service. But then you have lot of overheads, because you can see that there are a lot of control messages in terms of acknowledgement. Okay, so additional protocol flows ensure that duplicate messages are not delivered. So you can see this is a combination of the QoS label 0 and QoS label 1. But you have to ensure that you do not send any duplicate packets. And also you have to ensure that only one packet that you have sent that is received by the subscriber. Okay, so the subscriber should get only one packet. So the flow is: publisher stores the message, it publishes the message, broker receives the message, broker then stores the message, it publishes to the subscriber, okay, and then it sends the received. So the whatever topics have been published, that has been received by the subscriber, okay, that information is actually sent to the publisher by the broker. Then the publisher releases that. Okay, so it sends a publish release control message, and then only the broker will delete the message. Keep in mind that the broker cannot delete the message until the publisher informs it. Okay. So broker will then delete the message. Once the broker deletes the message, then it informs the publisher, and then the publisher deletes the message. So you can see the number of control messages is much more in this case as compared to the previous quality of service levels 0 and 1. Okay, so if you have a very high performance application or highly sensitive application, you can go for quality of service levels 2. If it is a day-to-day application where you are only simply recording temperature data, pressure data, and you just want to monitor the scenario, then quality of service level 0 is fine, because even if some packets are getting dropped, you don't worry about that. So that is how the quality of service is defined. And based on the application, you have to define the quality of service. Okay. So far I have talked about the first protocol, that is your message queuing telemetry protocol. And we saw that this is the simplest protocol. And if you look at the quality of service, or if you look at the payload, if you look at the flags, they are very straightforward to handle in terms of data frames. Okay. But then let's see some other sets of protocols which have been developed looking at different kinds of performance measures, different kinds of application requirements, where security also comes into picture. So the second set is the second protocol is AMQP, which is called as Advanced Message Queuing Protocols. So in the name itself, you can see there is a queue involved. So there is a queuing process. It is more secure, okay, more compact, more symmetrical, multiplexed, reliable binary transfer protocol. So as compared to MQTT, of course, this is much better, but then the complexity is also high. We'll see why the complexity is high. So similar to other protocols, you can move the messages between applications, okay, considered by JP Morgan in 2006. This is a layered model. So you have a transport and security protocol, and then you have a frame transfer protocol, and then you have a message transfer protocol. Okay. These are not tied to any particular source or any targets. There is no predefined topology also. Okay. Of course, when you compare this one with the MQTT protocol, the conventional message brokers can also be handled in AMQP. In fact, they can be made a part of the AMQP also. In addition to those scenarios, you can also handle higher infrastructure requirements in terms of let's say a complete big industry, big building, big area network. So all those can be handled in terms of AMQP as compared to the simplest application that we looked at in the previous case. So you can see why AMQP is popular as compared to MQTT. So if you are dealing with different organizations, so if your data is being shared between multiple organizations, then AMQP can be brought in. If you have different kinds of technology, okay, so we have different kinds of, let's say, some telemetry, some communication, some different kinds of technologies, then also AMQP can come into picture. If you have different organizations with respect to time, so if you are dealing with different organizations and the data has to be communicated over different time units, okay, different time zones, then also MQP helps us. And if you have different technologies as well as organizations located in different locations, then also MQP helps us. So you can see the bigger impact of AMQP in terms of how they handle the structures or organizations. Rest of this are, of course, advantages of AMQP. Here, we'll also look at the protocol architecture in this case. So this is how the AMQP works. So you have a publisher application and you have a consumer application. Okay. Instead of a broker that was there in the previous case, now we have a server. Okay. And this server is more like an exchange. Okay. Uh, when we look at the server, this is a virtual host. Okay, so the virtual host can change at any time. Okay, it does have an exchange which collects the publisher topics, and there is a message queue, and depending on the consumer queue, depending on the queuing strategy that you follow, based on that, the topics are actually provided to the consumers. Okay, so instead of the conventional broker that you saw in the MQTT case, now you do have a exchange or a server which acts like a broker. So let's look at the details of these exchange, what exactly this exchange is doing. So you can see that you do have a container node having a client, okay, and let's say that is a producer's consumer, depending on whether it is a publisher or a subscriber. On the right side, we have the broker, which is handling the queue. Okay, and you establish the connection, you establish the session, you establish the link, and then the queuing strategy is deployed to find out which consumer would get the first topic, which consumer will get the second topic. Right? So in the second figure, you can see examples of messages. So for example, if you look at the broker within the exchange, you have different kinds of bindings and you have different kinds of queues. Okay. Now, when you form these queues, for example, USA.has is one binding key, has.news is the second binding key, has.weather is the third binding key, and the fourth binding key is Europe.has. Okay. So based on the messages, for example, the first message routing key is USA.news. Okay, and the second routing key is USA.weather, and you can see that both the routing keys, the binding key USA is common. Okay, so both the routing keys are now referred to the same queue, that is USA.has. Similarly, wherever you have news word common, they go to the binding key, that is has.news. Okay, so based on the common key that you have, based on that you will connect to some kind of queue. And then this no, in the queue you have, say for example, these are the four binding keys that you can decide what kind of strategy you want, and based on that, say for example, first come first serve basis, you decide the queuing strategy. So based on that, you can release the topics. So what exactly this exchange does? Now, here the exchange acts as a broker. Okay, so let's see how this exchange is better than the previous broker that we dealt with when we discussed about MQTT. Now, again, this is acting as a message routing. Okay, so it acts as a message router. All those advantages that you have, it's durable. Unless you delete it, it will continue. It is temporary. It lasts till the server shuts down. It lasts till no longer used. All those exchange properties are available. Uh, I told there is no, there are various ways that you can deal with the queue. So there are several type of exchanges: direct exchange, fan out exchange, topic exchange. Okay. Each message is delivered to each qualifying queue. We saw, you can see on the top the messages and you can see the queues. So if there is a word like USA, it has to reach the queue of USA.has. Okay. So each message is delivered to each qualifying queue, and the binding is the link between your queue and exchange. You can see the binding key is USA.has, right? So your exchange and your queue, they are bound by the bindings. Okay, so the binding key is USA.has for the red color one, right? Now, when we look at this AMQP protocol, you have multiple frames being multiplexed. So you have different organizations which are connecting at the same time or at different time zones. So how those are handled, you can look at this example in the topic exchange. So for example, USA.news, say somebody wants to read the USA news in India at morning 9 o'clock, and let's say somebody is going to read the news, let's say in US after a few hours. Okay, so in that case, since both the users have subscribed to the same topic, that is USA.news, although the time zones are different, the binding key ensures that both the topics are, the topic is available to both the users. Okay, so even though the time zone is different, the exchange makes sure that the same set of topic is available to both the clients or both the users. Okay, so that is the reason that time zone or physical layout doesn't affect this protocol. Different organizations, different time zones, it doesn't have any impact as far as this protocol is concerned. So that is the second protocol. The third protocol is the constrained application protocol. The reason I'm touching upon one or two high-performance protocol is, down the line, you will see that when you actually look at a practical application, neither MQTT nor AMQP alone would be able to satisfy all the requirements. So depending on the link and the requirement in that specific link, you use different kinds of protocols. So the third protocol is COAP, that is your constrained application protocol. This protocol was actually designed looking at the application specifically. Okay, so the constraint is with respect to applications itself, and these are more suitable when you look at resource constrained devices, because these are extremely lightweight protocols. But then the design is such that they have functionalities which have been designed looking at specific requirements. These are implemented over your UDP protocol, user datagram protocol, and these are well suited for limited capacity communication. Web transfer protocol is the REST. So if you look at the conventional HTTP protocol, on top of that, we do have a REST protocol which gets combined. This is a hybridization of REST and HTTP protocol. So there is a client and server architecture which deals with this COAP protocol in terms of specified application. Okay. The last one is the COAP modifies some functionality. Okay, I told you this is more linked to the application, so it modifies the functionalities, low power consumptions, or if you have a lossy link, then these protocols can be configured to deal with different kinds of applications. Okay, so if you have a low power application, you modify the COAP protocol for that application. If you have a link, the communication link which is more faulty or we have more loss, then you can modify the properties of COAP. So the COAP architecture is shown here. So you have the conventional HTTP communication, which is your internet server to your COAP proxy server kind of. Okay, so that is the conventional communication between your server and your internet. That is the HTTP. But when it comes to the internal architecture of the COAP environment, then you can see that you have different clients and you have a server, and that server is getting connected to a proxy. Okay, so here a proxy shows up. That proxy is actually handling this set of clients 1, 2, 3. Okay. The server is not directly connected to the REST internet, but rather the COAP server is connected to a proxy, and then the proxy is connected to the REST internet through the HTTP communication. So you can see if you look at the architecture is simple, but then this is very, very application specific. So you have a reduced overlay. So because you are modifying the properties based on the requirement, so the overhead is less. Parsing complexity, of course. But second one is application specific. So content type. So depending on the content type, you are modifying the properties of COAP. Support for discovery of resources is also provided. Subscription is simple, and caching mechanism is based on what is the maximum message age. So if you have sent a message which is existing for a longer duration, then that thing would be cached in the server. Okay. So there are two layers here. One is the messaging layer. The other one is your request and response layer, which is kind of you can say overhead kind of scenario, where the actual messages are put up in one sub layer, the other acknowledgement, other things are put up in the other one. So the messaging sub layer detects the duplications and provides reliable communication. The second sublayer is your request and response, which deals with the communication. So there are 4 types of messages here. Remember that the protocol is designed looking at the application. So the first category is you have a message which has to be confirmable. That means the message has been received by the client and it has to be confirmed. So it is a confirmable type of message. The second message is non-conformable. That means, it is not conformed to the publisher that the message has been received. Third one is the command kind of scenario, that is you reset the network. And fourth one is acknowledgement for any kind of message. Okay, so these are the 4 sets of messages that you have in the COAP. The fourth one, I'll touch in brief, and then I'll show you the case study that we performed in our lab using conventional Raspberry Pi microcontrollers and few temperature and pressure sensors. Okay. So the fourth one is your XMPP, which is extensible messaging and presence protocol. So conventional message protocol, but it does have advantages in terms of performance, in terms of data, in terms of latency. It does have advantage, but then complexity wise, you have to deal with a bigger set of equipment. This is also popularly known as Jabber. If anyone has used, this is very, very popular in terms of the chatting protocols. So example is Jingle extension allows for video and audio. So you have video and audio, both are allowed using Jingle extension. XML is used. XML is the conventional extensible markup language that is used in this case. The important part is this is a real-time exchange of structural data. If you go back to the MQTT, there was no requirement of subscriber and publisher to be connected in the same time. Right? So, but this is a real-time exchange of structural data. So wherever you have a requirement of real-time communication, then this XMPP can be deployed. Wherever there is some delay can be managed, then I can go for the previous 3 protocols. This is an open standard protocol. Of course, client server architecture comes into picture. Okay. This is more decentralized because you can, you'll see that in this architecture there is no central server. So the devices or the clients can run their own XMPP server. Okay, so every client can design its own XMPP server, so it's very decentralized. This is a open standard, so you do not have you don't have to pay any royalties or any you do not require any permissions. Security is something which has been included in this protocol. So you require authentication and encryption. The other protocols that I talked about, for example, MQTT, the conventional MQTT protocol doesn't require any authentication. But if you want a high security, there is a variant of the MQTT which is called a secured MQTT, MQTT sec. So MQTT-sec, that is security. So that is a variant of MQTT which includes higher security standards compared to conventional MQTT. But this XMPP has inbuilt authentication and encryption. Flexibility-wise, it supports interoperability. So it is it handles various kinds of devices. We'll see in one of the architecture figures. So here is the XMPP architecture. As I said, any device, any client can act as a XMPP server. So you can see at the center there is an internet. There are clients who themselves can act as XMPP server. So you do not require any centralized server in this case. So each client can act as a server. Two clients can combine and act as one of them can act as a server to transmit the data. So that is how they can get connected to internet. And the other part that I mentioned is you can handle different kinds of clients. So here you have SMS clients, you have audio clients, you have video clients. So you have SMS client that is connected to SMS server, and then you have XMPP gateway, which is connected to the internet. So the architecture is much more decentralized. Anyone can act as a server and can pass the data. But this, since multiple technologies are involved, each client can become a server. So that is why the authentication and encryption part is much more incorporated in this architecture. So if I compare the four protocols in terms of theory, okay, so these are the 6 different properties that we are comparing. So we started with MQTT. If you look at the quality of service, all 3 quality of service are retained. Okay, whereas when you look at XMPP, because every client can act as a server, so the quality of service is actually left to the client. You do not handle, the protocol doesn't handle any quality of service. Okay, so the support to the quality of service is not available in XMPP. Security wise, we have SSL in 3 cases except this UAP. But then the amount of security that you find in XMPP is much high as compared to the other 3. Bandwidth needed, of course, except AMQP, where the broker comes into picture, where the exchange comes into picture, that is where your bandwidth requirement is more. Rest other cases, the bandwidth requirement is low. Okay. Of course, the message caching property is available in each protocol. Whether the protocol can discover the new clients or not. So in MQTT, you cannot discover a new client. The client has to subscribe to certain topic. Then only the broker knows that, okay, this is a new client. So you cannot discover if a new client shows up. Okay. Whereas when you look at COAP or XMPP, because for example, XMPP, each device or each client can act as XMPP server. So I can directly connect to the internet and automatically as a resource, I am discovered. Okay. So that is the reason the resource can be discovered in COAP and XMPP, whereas it cannot be discovered in MQTT and MQP. And the last one is what kind of whether you are using TCP protocol or UDP protocol. Based on that, the types of service are defined. Okay. So let's look at a experimental setup that we made in our lab just to compare the four protocols. Okay. So what we have is simple temperature sensors, very low cost DST-11 temperature sensors. So, and the temperature sensor data is acting as the payload. And we connected these sensors to Raspberry Pi microcontrollers. Those act as publishers. So whatever information is collected by these sensors, those are stored in the Raspberry Pi, so they can publish the data. Okay. Let's say the Wi-Fi is the medium of communication. Okay, and let's say a computer is acting as a subscriber. So let's say I am interested in the temperature information, but from only the temperature sensor 1. Okay, so I'm subscribing to only temperature sensor 1. So what would happen to the protocol? Okay. So this is the experimental setup that we made in the lab. And for comparing the four protocols, what we did was, for example, for MQTT, we require publisher and subscriber. So Raspberry Pi act as the publisher and my computer act as the subscriber. Similarly, for the AMQP, Raspberry Pi act as the publisher application and computer acts as the consumer application. COAP, client 1 is Raspberry Pi, client 2 is computer, and XMPP, both of them, Raspberry Pi as well as computer, both of them are clients, and they can make themselves XMPP server and communicate among themselves. So for XMPP, you do not define individually; they both can act as XMPP servers and communicate. So let's look at the results. So when we look at the amount of time that is required to create the packets, okay, so the packet creation time for protocols, the unit is microseconds. Okay. Now I have already said MQTT is the simplest protocol that you have. So the message format is simple. You have a fixed header, you have a variable header, you have a payload. So this complexity is very, very low. How much time is required to create these packets? So MQTT requires the least amount of time to actually create these packets, whereas if you go back to the AMQP or COAP, they require more time as compared to MQTT. But the last one, XMPP, that requires the highest amount of time because the client themselves handle the communication, right? So there is no exchange involved here. So both the Raspberry Pi and the computer, they have to act as clients themselves and communicate among them. So to design the frame, to design the packet structure, to design the payload, all those things have to be done by the client. Okay, so that's the reason that the amount of time required in XMPP is much more. The second one is, the first one was how much time was required to create the packets. Now the second one is how much time it took to transmit the packets. Okay, so packet transmission time protocols. Here also you can see that if you are using this MQTT, which is the simplest one, then the amount of time that is required is very, very low. In fact, if you look at AMQP and COAP also, the amount of time that is required for packet transmission is low, of course, more than MQTT. But XMPP, you require a lot of transmission time because, as I said, there is no one involved as an exchange or as a broker. Okay. So the amount of time that is required to generate these packets, to transmit these packets, is much more in XMPP. As far as message size is concerned, of course, COAP has the list size, followed by MQTT. Then, of course, your AMQP, and XMPP will have the highest size, as I have to design everything, assuming that I am the server. So all structure have to be designed accordingly. Okay. So the last slide shows you the the overall architecture that can be used for practical applications. Okay. So here is an example where you can see that there is not a single protocol that you can say that it is enough for handling all the applications. So for example, this is a complex use case. Let's say you have a cloud, okay, and the cloud, there is a PC which is connected to the cloud. Let's say there is some gateway which is connected to some sensors. There are smartphones, there are tablets. Okay. So there are a lot of devices which are connected to each other, okay, connected to the cloud. And if you see the structure within the box, that is your gateway is connected to the sensors. I can use MQTT, which is the simplest one, or I can use MQTT secured one, or I can use AMQP. Okay, both of them can be used as protocols for communication between sensors and gateway. Okay, which is, as I said, if you're interested in temperature information or pressure information, so in that case I can change the quality of service flag, and then I can send it from the sensors to the gateway. Okay. So based on what kind of quality of service is required, I can always modify the properties of the QoS flag. Okay. Or I can also go for AMQP, which is again more or less, we looked at the, so if you go back to the previous results, you can see that, AMQP performance as compared to, the transmission time, or you can say message size, is not very high as compared to MQTT. Whereas XMPP has a very high message size, transmission time, all those things. Okay. So as far as the sensors and gateways are concerned, they can be easily connected using the simplest low-cost protocols, which is your MQTT, or somewhat better performance is achieved through AMQP. But then these gateways, they are supposed to be connected to the cloud. Okay. When you are connecting these gateways to the cloud, then I do not prefer MQTT, because then the security aspect also comes into picture. Okay. And then there are multiple devices. I require some kind of queuing strategy, right? And these gateways. So for example, sitting here, there might be another gateway operating in another city, and I want to switch on the device and switch off the device, or I can, I want to manage the devices through the gateway, right? So different organizations, different time zones, different categories of applications. So in those scenarios, I do not prefer MQTT. I would preferably go for AMQP or higher standards for communication between gateway and cloud. Okay. But then when you look at your PC, and if your PC is getting connected to cloud, then also I do not want to get into MQTT, because although that is the simplest protocol, the security aspect of this. Let me go back to the security part. Okay, so if you look at the security part, your MQTT as such, although it is SSL, but the amount of security that you can have in the AMQP is much more than your MQTT, and in fact, that is the reason that it has a high bandwidth. Okay, because of the payload as well as the security standards. Okay, so you can see that the communication between PC and cloud, that is not happening through MQTT, but rather AMQP. Or of course, you can deploy your the XMPP or higher protocols. Okay. Similarly, when your smartphone or tablets are getting connected to the cloud, okay, so in that case, I do not require MQTT or AMQP, because in that case, I can simply fall back to the conventional HTTP protocol, right? I can for example, you are browsing over your smartphone, or you are browsing over your tablet. I can always go for the HTTP or HTTPS secured protocols. I do not require these MQTT or AMQP protocols which deal with the payload kind of data. Okay, so that is why the protocols are different for smartphones and tablets. In the cloud, you can see that the cloud is such that it should be able to handle AMQP. It should also be able to handle HTTP protocols. So the cloud would be able to handle all four protocols. Okay, there could be some devices which are directly connected to the cloud through MQTT. Of course, the security aspect has to be taken care of. But for all rest three protocols, even though you are getting connected to the cloud, the cloud should be able to handle all four architectures simultaneously, because remember, the data can be sent from all these devices in real time simultaneously. So that has to be taken care of. Okay? So that is why I have pointed out in the conclusion that your protocol choice, it depends on what kind of application or what type of scenario is there, right? Here itself, you can see the different kind of scenario. Sensor to gateway scenario is different than gateway to cloud scenario. Okay, gateway to cloud scenario is different than your tablet to cloud scenario. So based on the scenario, you have to choose the protocol. We saw that all the four protocols have different advantages and limitations. Some are useful in terms of real-time applications, sometimes useful as far as the queuing is concerned. Sometimes you do not want to, you want low-cost applications. So in that case, you fall back to the conventional MQTT protocol. Okay, so based on the complexity of the application, you can design the protocols. Okay, so keep in mind that all the four protocols have their pros and cons, and not a single protocol has to be used. It has to be a combination of all the four protocols. Okay. So I think that's all. These are few references. In fact, I have highlighted the references based on the way that I have covered the protocols. So the fifth one is the standard MQTT protocol website, that is mqtt.org. Okay. So this is where all the MQTT related standard information is available. A few 1 to 4 gives you basic idea of strategies, protocols that were initially designed looking at IoT. Sixth one is the MQTT application. Okay. Seventh one is again MQTT for device automation. Eighth one is the second protocol, that is AMQP. It does have its own website, so amqp.org. You can refer to that. One of the popular, you can say, servers that you use for implementing these protocols is RabbitMQ. In fact, we have used RabbitMQ for this case study and for for comparing for designing other IoT applications. Also, it does have certain number of certain limitations as far as the number of devices that you can connect. But this RabbitMQ is very good in terms of client libraries, tools. So if you want to just have a go at the protocols with a simple example, you can actually use RabbitMQ and use the existing libraries and compare the protocols. 10th one is a very popular talk related to RabbitMQ. It was a talk at Google. So if you are interested, you can have a look at this RabbitMQ talk. 11th one is the third protocol, that is COAP, Constraint Application Protocol, application specific protocols that we designed. That is also available online. You can also go to coap.me, that is 12th reference. And fourth one is the XMPP protocol. So xmpp.org is standard website available for XMPP. And if you want to look at the results that I have shown for the case study, you can look at one of our publications in IEEE Embedded Systems Latest, where we have deployed these protocols and compared these protocols, and you can see. In fact, these are very low cost experiments which can be carried out in the lab. I mean, you require hardly 2-3 Raspberry Pis and let's say 3-4 temperature or pressure sensors. That should be enough to compare all these protocols. So if you want to have a go at these protocols to look at the performance, you can just probably within an amount of 10,000 or 15,000, you can build the setup and compare the protocols. So I think that's all from my side. Thank you very much. Now I am open to any queries or any should I